2 years ago, and among many other developments, she has been working on using MPAS, testing it and integrating into the Vortex modeling system. So I saw you for a second there, Marta. So hopefully you're sharing your screen now.
Yeah.
So your title is A Seamless Avenue to Drive Wind Resource Time Series Modeling, the MPAS model and the mesoscale reframed. So there you go, and this you have half an hour.
Okay, perfect. You can see the presentation,
yes,
right?
Good. Yes.
Perfect. So hello everyone, thank you for attending this session. My goal is to introduce a new mesoscale model, which may be the future in the wind resource assessment modeling. Right now, the weather and research forecasting model, WRF, is widely used in the industry, and it's the preferred method to go from the macro scale to mesoscale or microscale. These years, the wind industry has benefited from improvements in both ends of the modeling chain. We have now better macro scale input data with reanalysis like ERA5, and we have better microscale models with models like WRF LES. So the question is whether is it time to change the downscaling method itself. So in this presentation, what I'm going to do is first introduce MPAS and explain a bit the differences it has with the WRF model. And I'm going to show a very simple first validation of some MPAS simulations and WRF simulations compared to real world wind measurements. And we are going to talk a little bit about which are the current limitations of the model and which things need to be developed and improved to really be useful for wind industry. So MPAS stands for Model for Prediction Across the Scales, and is a collaborative project led by US research centers that aims to establish a common framework for atmosphere, ocean, and other Earth systems models. The atmospheric part is being developed by NCAR, which are the creators of WRF. So it will inherit many of the features that WRF already has. So one of the most defining characteristics of MPAS is its space discretization. Instead of using a Laplon grid like WRF, it uses an unstructured 2D horizontal grid. That is to say, there are cells which are set in some latitudes and longitudes. And what this set of cells follows is that it's a mathematical construction called spherical centroidal Voronoi tessellation. No need to go into details, but it's basically some hexagons or pentagons and heptagons too that cover all the globe and have special properties that will make them very useful to solve the equations on them. With respect to the vertical coordinate, it's structured. It's levels that we are used to in WRF, and they can be set by default, or you can decide how many levels do you want. And it uses grid staggering like WRF. That's to say that wind speeds are computed at the edges of the cells, not at the center. And afterwards, the MPAS model itself can calculate which is the meridional and the other one, velocities. So the generation of the meshes is done by an iterative process, which is probabilistic. And once you define a density function that you want that the mesh more or less follows that distribution, then it's a probabilistic process, which is very long, and finally converges to some mesh which is almost that mathematical structure, and then it's a valid mesh that can be used in MPAS. And this MPAS doesn't release this mesh generation tool yet. So what we can use are those meshes that are available for download. And we can divide the available meshes in two parts, which some meshes are quasi-uniform meshes. That is to say, they are partitions of the globe, which every cell has more or less the same size. And then in that way, you can more or less decide which is the resolution the mesh has. And they have options from 480 kilometers to 3 kilometers resolution. And then more interestingly, we have variable resolution meshes. We have meshes for some area, some circular area normally, or some a little bit elliptical. Some area has higher resolution, so the cells are smaller. There's a refinement there, and then it slowly grows and it gets to lower resolution and bigger cells. And these meshes can be rotated, so you can center the refined part in the part of the globe where you want to run the high-resolution simulation. Also, these meshes can be partitioned, and then we can have parallel computation, which is something that it won't be explored deeply in this presentation, but it's definitely something that in the future we want to go deeper. In version 7, so only last year, there was the limited area simulations were released, which is something which is essential for wind resource assessment, so it couldn't be tried until now. The idea with these simulations is that you can cut some region from a global mesh, and then this mesh that you have cut can be variable resolution, and there can be a refinement. And then the boundary conditions are going to be updated with reanalysis data, which is going to be from the resolution that the mesh has at that part, more or less. And then there will be a seamless interaction between scales until you get the part that you want at the resolution you need, which has been updated very smoothly. That would be the idea of using these limited area simulations. So the things I explained till now are common for all MPAS cores, for oceans, for every Earth system. But we are interested in the MPAS atmosphere, right, which is going to be designed by WRF and by the same creators of WRF. And it contains mostly the same dynamical core, the same physics, only like stripped bare, and they only kept one of the things that they felt were working better with WRF, and they started with it very simply. And in the future, I think they are going to add more suits and more methods. But right now, let's say that the physics part and the dynamical core is very similar to WRF. It's the same idea, it's just reframed in a new system with new meshes and new rules. And so the thing is, why would the creators of WRF be interested in creating a new model? And there are some things which are the creators have been seeing that are disadvantages or limitations that WRF has, and they think MPAS can be the answer to that, right? So there are some deformation due to projections, for example, or basically that when you want to do higher resolution, you have to do nesting, and this has a flow distortion at the nest boundaries that may not be what you are looking for. And also, MPAS was also very focused on global simulations, which is something that in WRF you have problems with the poles. So MPAS in that way was very good. And this is something that they are still working on. Sorry. Okay. So what we are interested in is into the wind resource assessment with this model. And when wind resource assessment, what you need is long-term wind data time series. So at specific locations or small regions. But the idea is that you need long-term data that are updated using the reanalysis, a very good reanalysis, and that you only need a small region. So
hello, Guy. Can you hear me? Hi.
Yeah. Sorry.
Hi.
You have any question or something, or I can go on?
Hi. New face. Nice to meet you.
Sorry, we have a speaker on now, so please mute your microphone. Only speak
Yes.
when there's a question.
Yes.
Thank you.
Okay, I will go on. What we need, the mesh that we require should follow some rules or some things that would be useful for us. So what we would like is to have a central region which had high resolution, because that's where we want our wind farm to be and where we are interested in the results. And then from this high resolution area, it should smoothly transition to low resolution, or the resolution that the reanalysis can understand. And also, we would like that it didn't cover a lot of area, that it didn't have a lot of cells, so that we don't have a lot of time in the computation, and it takes shorter time. But we are not there yet, so we cannot generate our own meshes. And the best candidate we can have from the ones that are available would be this one that goes from 3 kilometers to 60 kilometers. And besides that, 3 kilometers is not very high resolution for our, I mean, maybe we would like to go even further than 3 kilometers. Also, the area that covers 3 kilometers, I don't know if you see it, it's more like the Iberian Peninsula. It's a very huge area at 3 kilometers that wouldn't be what we would need if we just wanted to assess one specific wind farm. And it has a lot of cells and it takes a lot of time to compute, and it's too time to consuming to do right now in our computers just to make a test. So it was not something that we could easily try. So, but we wanted to try something. We wanted to have a first idea of how MPAS and WRF can be compared, or if there is a lot of differences, and just to get an idea of and a feel of how long it takes. And what we did was to choose 23 sites around the world, and we ran 4 simulations by site. These simulations all had in common that they were 1-year simulations. They were split in days, so every simulation was 1-day simulation. And then that we used ERA5 reanalysis because it's the reanalysis that we trust the most. And we did 2 simulations with MPAS and 2 with WRF. The ones are MPAS, both of them are circular regions that are cut from a quasi-uniform mesh. So of course, quasi-uniform mesh, that's not what we would like to try. We would like to try a variable resolution mesh, but as we said, that was not feasible to do at this scale. So we had to try just quasi-uniform mesh, and we tried one of which was 15 kilometer resolution and 10 kilometer resolution. That we need to remember that they're going to be fed with ERA5, which is more or less 30 kilometer resolution. And the one of the simulations, the one that's done at 15 kilometer resolution, it's the circular region has a radius of 200. And in the one that's at 10 kilometers, the circular region is 150 kilometers. And then we did 2 simulations with WRF using our standard vortex parameters, the simulations that we trust. But we did them at 9 kilometers, so no nesting and nothing, just 9 kilometers straight from the reanalysis. And what we wanted to try was to compare if nudging did something different, or how nudging helped or not or didn't to MPAS. So nudging is this option of a model where you can use the reanalysis values to change the values during the simulation, inside the simulation, not only as boundary conditions, which makes the simulations be more similar, or like you establish that WRF cannot go freely to change a lot. It has to more or less go to the values that the reanalysis say. So it's a more controlled simulation. And this option is not available in MPAS, at least yet. So we wanted to try if WRF without nudging, which would be like MPAS, was better or worse, and how did the nudging improve this picture. Okay, so I'm going to show the results now. So this first slide is the bias. In the first picture, we can see the mean bias in relative quantities of the mean wind speed, of course, for different sites and the 4 simulations. And in the other one, it's the mean absolute bias, okay? And we can see that the bias is quite high. This is expected because the resolution of these simulations is between 9 and 15 kilometers. At this resolution, when we compare with real-world data, we expect there to be bias. So that's what wasn't something that we were too worried about. But it's interesting to see that both MPAS simulations have quite the same shape, have the same spread, and that this spread of results is quite bigger than WRF. So that's something to take into account. But more interestingly, we wanted to look at the correlations to see if this better integration between scales helped something. And it was good to see that both MPAS simulations correlated better than the WRF simulations, even when the nudging was applied, which maybe was something that could help the simulation go in that way. But yeah, MPAS gave very good results, especially monthly. We were very surprised to see if you compare the MPAS green and blue plots with the orange one, which is the WRF without nudging. We can see that WRF without nudging was a bit lost in some places. And if we can zoom that information, and what we are going to see here is for each of the sites, for each of the 23 sites, which is the monthly correlation for each of the simulations. And what we can see is that there are 3 sites. I don't know, I cannot see the numbers, but the 4 and the 15 and 10, where we see that the WRF without nudging is horrible, gives resolutions worse than 0.4, and that when we use WRF with nudging, it improves a little bit, but the MPAS simulations perform significantly better without this nudging having been applied. So that was surprising and very good information. And if we see there's another case in the station 0, which the opposite is happening. We have the WRF without nudging was the one that had better correlation, while the other 3 were doing completely wrong. So this is definitely no big reveal that MPAS has better monthly correlations than WRF, but it's something that can let us think, and we can want to explore with new tests if this actually means that MPAS can have the potential to capture long-term information better than WRF did. With respect to computation, we have to say that this test was done in our cluster, in our typical cluster. So we only used 1 core when MPAS is prepared to be parallelized, and we have to make, we are preparing some tests to see how it scales. But in this case, it was just done 1 core, as we would have run WRF, the same system we use normally. And in using 1 core, MPAS does not go faster. It doesn't go much slower, but it's kind of in the same order of magnitude. And this is something that maybe could be improved afterwards with other tests. So just now to wrap it up, there are some limitations that we have said about the available meshes. For example, only go until 3 kilometer resolution, and MPAS itself and the physics are not ready yet to integrate with LES or to go to finer resolutions. So that would be something that would be a limitation right now. And right now, if we want to make limited area regions, we still don't have meshes that have a reasonable number of cells so that you can start making tests and trying a lot of sites. And there's no nudging. And in 1 core and without parallel computer, MPAS will not go faster. So these are some reflections about some of the things that right now wouldn't make it possible for us to change from WRF to MPAS and change everything and use this new model. But there are some interesting ideas that we have found in this test, which is that we have these excellent monthly correlations that make us think that MPAS may be the way to go, and that once we have a measurement tool and we can try win sites that are interesting for us, we may have good potential there. And afterwards, that of course doing this in parallel can be the key to making more tests and being able to use it widely. So the thing is that there will be new versions of MPAS, and we have to follow the development, and we are very interested to understand if it will be better than WRF. But for now, WRF is here to stay, right? It will be just some model that maybe to the future of Windows assessment will be the leader. But right now, we have to wait yet. So I hope it was interesting, and thank you for your attention. And if you have any question or something you want to share, I'd be happy to answer.
Thank you very much, Marta. It was very interesting, and yeah, I wonder if there are any questions from the chat, or there's nothing yet I can see, or if anyone wants to raise a hand. In the meantime, oh yes, there is one. Sam Williams. So the question straight in from the chat. Thanks, Sam. Yeah. Do you have any sense of the timescales for MPAS development, i.e., when is it anticipated that the limited area models are released, etc.? Question mark.
So the limited area was released on June last year, and I went to the tutorial they do in NCAR to share what MPAS is on this, and I understood there that this year we were expecting a new version, which hasn't come yet. They usually came in June or in late spring, but I think maybe with the COVID situation, this has been delayed for a while. So I don't really know when the new version will come, but since it's already been more than 1 year since version 7 came, I wouldn't think it would be long. I think in a few months we can have a new version with new possibilities and new capabilities that may be interesting to try.
Thank you. Any more questions? Sam says thank you for the answer.
You're welcome.
Whilst the people may be thinking, I've got a question. You were saying about the meshes that are better appropriate for wind resource assessment. What would be kind of for you the kind of ideal mesh for you to have at your disposal?
Yeah, that's something I've thought. I mean, for me, I think the ideal mesh would be some mesh that had high resolution at the center, I won't be too ambitious and ask for 100 meters, right? But maybe 1 kilometer or 500 meters, something like, it's still not micro scale. And then that smoothly, because it has to be smooth, but as fast as possible, it goes to high resolution, to low resolution, sorry.
Yes.
So that the area that we have at this high resolution of interest would be a very small area, like the one in WRF where when you do a lot of domains, the one that you stay at the end, just, I don't know, cannot say the northern lines, but some small area.
Yeah.
And then in that way, you optimize the numbers of cells you need, and then you get the result at high resolution without doing a whole country simulated. I think that would be the mesh I have in my head, but and it's feasible, right? It can be generated, I think, once we have the tool.
Okay, there's another. Thank you, Marta. There's another question from Irving Gersang, who asks, for downscaling to wind resource grid level, MPAS will be even less relevant than WRF, right? So is that because? So Irving, maybe you need to clarify if you mean because it's not regular. Is that the issue? Resource grid.
What do you mean with relevant? Yes, exactly. I didn't quite understand.
If it's possible to just write a 5-line clarification, or you can actually, why not unmute and listen?
Unmute.
Yes, the regular cells. Yeah, I forgot we had that capability. So it means because it won't be a grid.
Because it won't be a grid.
Yes. Yeah.
Well, of course, once you have this unstructured mesh, the same way that you have a WRF mesh, which is not exactly the lat-long ideal thing you would like to have, then you have to you need to have some software that MPAS has created already, to pass from that hexagon grid to some regular grid that you want or that you're interested in, and this is a process that has its complications, but it can be done, and it's something that they are perfectly aware that people are going to be interested in changing to a standard NetCF grid.
So it's not a showstopper, really, with the.
I think it's not a showstopper. Maybe for usability or something, but at the end you just pass it through the software that we'll put in a regular grid. And I mean, even MPAS does the conversion of the wind. It's done automatically by MPAS. It's not like WRF that you have to do it afterwards. Here it's reconstructed already from the horizontal and the vertical dimensions. So that's something that's already done there. I think.
Good. There's one more question, and then we'll close the first part of this session. So thanks. This one comes from, I think it's Elodie Martin. Are the current Vortex products mainly maps 3 kilometers to 1 kilometers and farm 100 meters based on WRF then? Could you tell us more? How is Vortex farm produced from Vortex maps? Thank you. So maybe the difference between those two products.
The difference between the products. Okay, so the products that we use are all done with WRF, because as I said, the meshes we have now available like MPAS don't make us. It's not feasible to change to use it with MPAS. Maybe maps, yes. So I think the difference, the basic difference within farm and maps is the resolution you reach, right? So in maps you stay until 3 kilometers, 9 kilometers, which allows you to make bigger areas and to have larger simulations. But as soon as you want to do some more nested domains to reach higher resolution, then you have a smaller area, and that would be a farm, which is better resolution, but the limitation is the space. So at the end, everything is a game between how good you want to do simulation in respect with the resolution, and then how much time you can spend doing the simulation. So it's on the computational power. So MPAS for us would be something to try to see if it improves our capabilities right now, and then we can offer better resolution and bigger simulations, and with better integration between scales. That would be great. But it's still very, very in development.
Thank you. So thanks, Marta, for the very nice presentation and a lot of questions. Thank you to the audience for engaging with these questions.
Thank you, everyone.
And Elodie says thank you. And we have now a 13-minute break. So it'll be starting again this session. We'll start again at 2:30 if you're in Europe summertime,